Hey everybody, so this lesson here, the next one we're doing, is about waves in 2 dimensions. And so we're going to look at ripple tank demos. So I'll show you what a ripple tank is. And so we're going to look at plane waves, how they reflect, a process called diffraction, and then another process called refraction. Refraction should be more familiar from grade 10 science in the light unit. I'll try to remind you of some of that stuff. And then interference, which is actually really standing wave patterns, but in 2 dimensions. So here we go. As usual, you're going to have the first page there for questions to do. I think there's 8 in total there. No big deal. All right, hopefully you're finding that anyways. I don't think the lesson takes like 20 minutes or half an hour, and then you have the rest of the time to work on questions and submit. I haven't heard of any issues yet, so let me know how you're doing. So this is what a ripple tank looks like. I'll load up the file there. Just give me a second. I'll show you what that looks like. And so basically, it's a tank with ripples in it. It's a shallow water tank, and then you can project light through it. And then as light goes through the waves, they actually focus, just like lenses, like it makes little convex lenses, like from grade 10 science, right? Little lines. And so you can see the waves as bright lines on the paper below. So it looks like that. So those are plane waves, nice straight wave fronts going along. Okay, and that's the idea. And that's really the exact same wave generator I have. There's different designs out there. This ripple tank looks different, but same kind of thing. Okay, so a lot of the videos you'll see just so you have an idea of what was going on and what happened. Okay. So with waves in 2D, the most familiar really is probably circular waves. If you throw a stone into a pond or something like that, you're gonna have ripples that are gonna go out radially as circles, getting bigger and bigger. And so if you're looking at plane waves, you can make those in nature too. With like if there's a log on the side of the lake, you can sort of jiggle the log and it'll send out a little wave front. If you're thinking of waves in 2D as just inherently being circles, it might be helpful to think of in some scenarios little ripples all lined up, forming a nice straight edge. Okay, so that's what you can think of as plane waves, all building up. And you can think of it as an example of superposition, really, right? All of those plane waves would sort of add up along that edge, making a nice edge. You're going to hear the name Christian Huygens later on in grade 12 physics when you're looking at the big debate between about the nature of light, whether it's a wave or a particle. And Huygens was a big proponent. He really felt it was a wave. And so this was his description, as to describe, how light can travel in a straight line rather than just radially always go outwards. It kind of basically is part of the complex discussion anyways. So how we see waves in a ripple tank, like I described, like goes through as a little, like focuses to a line, a bright spot, and acts as a lens. Okay. So here's a video of circular waves. So videos here. Circular waves. So literally just hitting the surface with a little ball and making circular waves. Easy, what we're looking at. And then plane waves. So plane waves. And I'll go back here. So this is a little pulse of a plane wave, and it's like I have to pause it and show you. Basically, you can see as I'm going here forward, the waves are going like down the page. So I should have done a slow motion, but you get the idea. They're going down the page, and so you can see the little clip of it going down the page, down the page, down the page, right? So actually, the YouTube version of the file, they probably put it in slow motion, but probably still works. Should do this. I'm getting dinged with a commercial from my own stuff, so that's good. Playback speed. Oh no. I made it so short. All right, here we go. Playback speed 0.25. if that's a little easier to watch. Oh yeah, winning. All right, so plane waves going along, easy to visualize those now and know they really exist and so on. So one thing to look at would be reflection of waves. And so if we sent in a plane wave in a direction like this, you'll find that it reflects out much like normal light reflection does in grade 10 science, where an angle of incidence equal to the angle of reflection. And even like a particle does too, like whipping a tennis ball against a wall. It's going to bounce and go in a very predictable path based on the angles, right? So that's what we're going to see basically. Okay, so reflection, high frequency. Let's just see how quick this is. I might just do my YouTube version videos. So this guy here, again, I'll slow it down here. And so we're going to see in here, hard to see what's going on there. So what you have is you have bright waves coming in this way, and then you have the much less bright waves reflecting and going out that way. So you want to visualize a ray, like a light coming in like this, or not light, but the wavefront coming in that direction and then out that direction. And so just focus on the bright ones first. So certainly the bright ones are going like down the page, right, down the screen-ish on a little bit of an angle. Right, I can follow one of them with you for you. Watch. Then going down, 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 right? And then if we start over, we look at the faint ones are going out as well. It's just a little hard to see. So what I do is I do a little pulse of it rather than a whole bunch, and then it's more obvious. So this one's going to be like the wave going in and then out, right? Wave going in and out, in and out. Okay, so reflection happens as you'd expect it would with waves. Okay? Even further, more here, when you have a parabolic reflection, parabolic reflection, as you would have seen or heard about in grade 10 light unit, where the light rays will go to the focal point. That was a solar heater. You might have heard of something like that in your grade 10 science lessons. This is a blast furnace, so sunlight coming in like this all reflects and goes to this chamber here and incinerates whatever's in there. So what we're going to see is, light coming in here would reflect, and light coming in there would reflect, and light coming in here would reflect. Everything reflects to a spot there, and you're going to get a superposition of all of the wave energy at that spot, all reflecting to that spot in focus. Okay, that's a mathematical definition of what a parabola is if you're interested, but it's really not necessary. But picture light coming in, or wave coming in here is going to reflect to the spot. And anywhere it's going to go to that spot. So here we go. So parabolic reflection video. So it takes a little bit to set up here. Back to this here. All right. So pause there. It's 16 seconds. So I'm going to slow this one down as well. So here we go. A little mess going on as I put the rubber hose in and get it shaped like a parabola. And I'll just keep going here. Eventually you're going to see, there we go, plane waves coming in. And then if you notice right here, there's like a flashing light. Okay, I'll go back a little bit. So the plane waves start coming in nicely right around now. You see this, you see that little flashing light around that area. And that's really the spot where the waves are adding up to a super, adding up to double their size and so on. I don't know if I mentioned it before, but a two crest coming together would be called like a super crest, a double size, right? And a two troughs coming together would be a super trough. So there's a spot in there that we can definitely pick out where it's kind of like flashing, and you can tell the waves are kind of getting funneled and channeled into that spot. So right there, a dark spot where it was like a super trough, and then a bright spot where it was a super crest. Yeah, and so I added in a link to this one here, all parabolic reflection. Folder. Parabolic reflection. This is more of like a simulation of it. So you can get a better idea what that kind of looks like. We got the simulation of a plane wave coming in, all the energy getting focused to that spot and then going out, right? And so basically it's going to go light and then dark and light and dark in that area. So like the flash of light is happening there. Okay? And that's really what we saw in my video. I used to sort of doubt myself on it because I thought it should look more convincing or whatever. This one here, let's go reflection, same folder. Very similar look. Old school. I'll even turn the sound up for you so you can hear the old reel, film reel going. So the old film reel, the parabolic pattern. So it's kind of neat there. They're showing the reverse of it, where the focus is, you sent out circular waves that actually send out a flat wave, which is amazing that they managed to make that so well, that flat wave going out. So what we're even talking about is a flat wave going in and then reflecting to the focal point, and that's what you're going to see here, right there. So they had it highlighted where that spot is, and you'll see it actually like flash, dark, flash, dark, flash, dark, which we did see in mine as well. That's the focal point of that. So all those waves are getting sort of funneled to that spot. So it's a parabolic reflection. So again, seeing waves do something that light does. And so if you think ahead to the grade 12 course, when you're looking at whether light is a wave or a particle, this is pretty darn good evidence of wave theory. Although of course, tennis balls would do the same thing, right? If you whipped a particle at a parabola shape, it's going to reflect and bounce off and go to that spot as well. So basically, Newton and Huygens could argue back and forth that both of them are explained by particle properties and wave properties. Okay? It's when you get to things that can't be explained, right? If light behaves in a way that can't be explained by particle or wave, now you've got some interesting evidence that should be considered in the big debate later on in grade 12. Excuse me. All right, so diffraction, possibly a new word for you, is the change in direction of a wave just because it's passing a barrier. It's a strange thing, but we can justify an explanation for this based on something we've said earlier this lesson. So I'll keep going for now. This is what you're going to see, right? So you're going to see plane waves going along, and then just passes a barrier. And so instead of it just being, a cutoff where it's just, the wave goes there and there's nothing else going on, what you're going to see is very obvious curves going out on an angle like that. Okay. And so, and in a case where there's higher frequency, you'll notice that it's really not as much diffraction happening. Okay. So with a long, low frequency, long wavelength, there's lots of diffraction. And with high frequency, there's a smaller amount. So high frequency, short wavelength, there's less diffraction. And so the way to describe this and sort of think about it in terms of wave properties is back to that Huygens wavelets idea. These little circular waves that really form this long straight wave. Picture one of those little circular waves there. End up with half of it not having anything else to combine with and cancel out with, and so it continues on like normal. And so that's your little Huygens wavelets, they call it, because that's what it's referred to as in the light unit in grade 12. So I'm just using that terminology. Why not? It helps explain the physical phenomenon that we're observing, right? So here's a quick little video of a long wavelength showing diffraction. So let's go replay, pause, and I will slow it down. All right, so plane wave coming along, and then look here. See these curves here, right? Nice straight waves, and then you'll see curved waves right there, right there, right there, right? Curved waves for sure. You've got diffraction happening. Quite a bit of curvature there, quite noticeable. I like to describe it as, if this is I joke around with my classes often that if I were to win the lottery, there'd be signs. One of the signs I fantasize building a physics theme park. And so there'd be a wave pool, if you will, like a pond or a lake or whatever, and you could like go out on little paddle boats or canoes or whatever else and ride the waves and so on. So basically there'd be spots. This one here, you'd be sitting in an area, you're behind a brick wall, you wouldn't think there'd be any waves. Big plane waves come through, people over here are riding the surf, and then you end up riding surf as well because of diffraction, right? Then in my physics theme park, I could crank up the frequency of the wave that's coming in, the frequency of the waves. And what would happen then is there would be less diffraction. And so you'd be in a canoe over here, hardly getting any waves. People over here would be going crazy, right? There'd be tons of waves, like, more often, more energy. They'd swear to you, oh my God, it was way wavier that time, way more waves per second and so on. Over here, you'd be like, man, I hardly felt anything. That's weird. Less diffraction because higher frequency, right? It would be just a really cool, large scale, hands-on experience kind of thing. So I like to just sort of mention the idea of it because you somewhat get the learning experience by even just thinking about the possibility of it. So diffraction continued. If we have waves going through an opening, then diffraction can actually lead to something interesting where you start out with plane waves and you end up with just circular waves. And again, that same description of thinking, okay, if this wave is really made up of a bunch of little curved wavelets that are all combining, well, at that point, then that curved little wavelet is going to go through there and it's going to proceed as an actual curved wavelet because it doesn't have anything else to cancel with. And so I really like the discussion of it as an explanation or a possible justification at least, right? And then, yeah, with longer wavelength, you have less diffraction. So you have a big straight section that survives with a little bit of curve on the end. There legitimately is like less diffraction as well. I don't know if that's really answered or explained based on the little wavelets, because you'd think there'd just be just as much bending on the edges, right, as before, just with a flat section in the middle, and that's not really what's seen. See this one here. So we have a plane wave coming in towards the boundary here, the barrier back here, and so that's the opening, I should say, and it's pretty obvious. You've got this nice curve, right? It's like someone's just sort of hitting here over and over again, sending out ripples in the pond, right? There's very obvious. I'll go even big screen here for you, right? It's very obvious, very circular waves coming out, okay, and nothing else really going on. Like if you were sitting here in a canoe in the theme park, you'd swear it was just a wave maker, of some sort, like someone dropping a boulder in here over and over again. Let's say, you can picture it would send out a circular wave like that. And the higher frequency one, my video or not? This one. So with a higher frequency, this isn't my video, but you have a big straight section, and then it kind of looks like there's just as much diffraction. So maybe I'm wrong on that. Maybe there is. It's just, basically the overall effect is less diffraction because you have all this other stuff going on, all the other straight wave section. But textbooks will definitely say there's less diffraction if the opening is bigger. And generically, too, you want to think of it as the bigger the wavelength is in comparison to the opening, the more diffraction there is. I apologize if I've said refraction by accident or not. I almost did just there. I don't think I have. So this is a phenomenon we're talking about in a physics class, right? In a physics course. If you see this in the world around you, don't be surprised. It does exist. So this is just a physical phenomenon. So picture water waves, ocean waves coming in, going through this opening, and ending up with a bunch of curves as a result. There's a spot on the highway near me where there's a culvert, and it'll be windy on the one side of the road, and waves are coming through, and then you just see like circular waves going off from the culvert. There's probably other effects going on, but it certainly looks like a nice example of diffraction. And so there you go. There's the curves there. This one's really cool. These little areas, there's a name for this. I forget what it is. Bifurcation barriers maybe, or something like that. But they make these little, little breakwaters. And so waves coming in diffract. And so you can see the curve pattern left on the beach. And it reduces the amount of erosion. It reduces the amount of energy of the waves hitting the shore. And so you end up with a big deposit of sand here. And, it's basically, the whole beach would have been eroded away way more if those weren't there, but boats can still go in and out, people can still swim and stuff like that. So along Lake Ontario, there's a spot. So we were going along on the train, my family and I were going to a Blue Jays game one time. I looked out the train and I was like, oh my gosh, look at it. And so I took some pictures of it, and then I ended up just going on Google Images, Google Maps or Google Earth or whatever, and and you can actually see these spots, and you can see the sand is actually deposited all the way up and meeting those barriers. So there's a ton of sand there that wouldn't have been there if it wasn't for the barriers and if it wasn't for the phenomenon known as diffraction. Okay, so those are all kind of examples of that. This one shows the idea that diffraction can sort of like heal the wave, if you will. If you have a barrier, obviously behind the barrier, there's not going to be as much waves. Eventually, going out far enough, it looks kind of like a normal wave, right? Because diffraction kind of comes together, and then you can picture these curves adding up and making a straight wave, which goes back to this idea of straight waves being made up of a bunch of curves. And you can see it sort of in action on that picture of a straight wave that is joining back together. Okay? And with longer wavelength, it joins back together quicker, right? Because there's more diffraction, less of a disturbance, obviously, too. So that's diffraction. The next one is refraction. So refraction is caused by the change in the speeds. So we talked previously about the speed of a wave based on the depth when we're talking about why waves crash the way they do going into beaches and shallower water. The speed gets lower, and so the wavelength has to get lower, and so the height of the wave gets bigger to compensate, to have the same amount of energy, and so on. And so ripple tank refraction, I'll go to the video lesson for that. Ripple tank. Tank diffraction, experiment 9, and so on. So in here, I need the volume down for this one. There we go. All right, so here, looking for one where we have where there's two different depths. This is not the one. Oh, because I typed in diffraction. Probably looking for refraction. That'd be why. Refraction. Here we go. So this one's going to have depths of water that are different. Okay, so there's actually a boundary there, and so you can see there's actually a change in direction. But first, I want to just focus on quite the right video. This is the one that's going on to the change in direction. Demos. Demos. Here we go. This is the one. Finally. So what we have is plane waves going along, and if you notice here, the wavelength. I'll just maybe pause. There we go. So the distance between the wavefronts is shorter here than here. So this is a shallow area, so it's going slower. So the plane waves come along, they slow down here, and they keep going normal speed here. Okay, what this is the ripple tank, and then this rectangle is just a piece of glass put in there, and so it's literally less deep because the glass bottom is higher up. So you can see the speed is quite a bit different, right? This wave front, fell behind to here, whereas the original wave front got all the way to there. It was going full speed. Okay, so that is just the change in the speed, right? Well, what happens is refraction itself is a change in the direction of a wave due to a change in the speed of the wave in the material, right? As it travels from one material to another, and it has to be at an angle of incidence to the normal, right? It's the full description of it. And so you saw stuff like this, hopefully in grade 10, where you have light coming in and changing direction. Beauty is now we can even maybe explain a little bit more about why, if you didn't have an explanation before. So if you think about this wave front right here, let's extend this one. Right, it would have gone to there. It was going full speed, but because it's in a slower material, it didn't go all the way to there. It only went to here. So it fell behind, right? And so it changes direction. It's pretty easy to think of why that happens when you see what's really going on and what's causing it. Okay, so that's refraction. There's there's diagrams like that all over the place, right? So we saw in this refraction, one of the refraction videos here. I may as well show that one again. So basically a wave coming in here, right? And then it's changing. So it's coming in kind of like this angle, and then it's ending up going out like that. So, they even trace in the angle it's going at, and then the angle it's going out at, and they look at the direction it's. It would be good if they showed like the line coming in and so on, that they're measuring the angle that way, which is the same as measuring to the normal, like we might have done in grade 10, hopefully did in grade 10. Yeah, so that's refraction. Kind of explained maybe a little bit more, and certainly, or at least anyways, we're saying like, hey, waves do this too. Light does it and waves do it. So again, as evidence of wave nature of light. These ones aren't as good, I don't think. Like, is that refraction or diffraction? I'm not really sure. It's a little harder to pin down in nature, I think. But maybe it's a change in direction of waves. It looks like there's a change there, right? So it could be because of depth. Could be because of depth. Yeah. Hopefully that makes sense. That's just another wave property that we know exists. And then finally now the interference pattern stuff. So what I have here is two wave patterns going out, and I have it drawn as you can see, like there's a trough and then a crest and a trough and a crest and so on. So the solid lines are crests or up waves, and down waves being the dash, right? And so if you take these two patterns and you just overlap them, like kind of like that or so, you can find spots where there's constructive interference and spots where there's destructive interference. Okay, so constructive interference. Let's use the green. I think these are infinite cloners here. They're not yet. Let me just fix that. Oh, constructive. This is an infinite cloner. There we go. All right. So basically, two crests, two troughs, two crests, two troughs. It kind of just lines up, and this is kind of supposed to be more like right in the middle, but it's just my drawings are a little bit lopsided. And then you got the two troughs, the two crests, the two troughs, and so on. And so you get these what are called nodal lines. Okay? You get nodes, which are areas that we in a standing wave pattern that don't have any movement. You'd end up with patterns of lines. So these are actually antinodes. Actually, I misspoke there. Those are antinodes because we got spots where they're adding up and so on. The destructive ones you'd see where you have a node and an antinode. So supposed to be off of center here if they're in phase. So the description, it ends up being like this if it's done carefully enough, right? We have an antinodal line in the middle. And the argument or the idea of that is it's antinodal line because if a crest got sent out and a crest got sent out, if you're exactly in the middle, they're going to arrive in phase. You're going to have constructive interference. Okay, that's the idea of why that is. So you end up with these nodal line patterns. And again, if you go to my physics theme park, if I win a lot of money, picture being on a body of water in little canoes or rowboats or whatever, and you could be in an area of a nodal line where there'd be no waves. Right beside you, someone's going up and down over waves, and then right after that, there's no waves again. Right, so no waves, waves, no waves. That'd be kind of weird. Right, you'd be experiencing destructive interference of water waves, hands-on. So the two up waves adding to a big up, or the two up down waves adding to a big down, right? That's what's happening here along the constructive areas. So it alternates between double up and double down, versus in nodal lines you have an up matching up with a down, or a partly up and partly down, adding up all the time to nothing. We have destructive interference patterns, and they're something that's just very easy to observe with ripple tanks. They just work. So ripple tank experiment interference, 10 maybe tank, and because there's a 10 in the name. And so this is just exactly that kind of thing where you have two ripples, going on and so on. And so what you have, if I pause this, is no wave is like gray. A wave up is bright, and then a wave down is dark, right? And so spots where it's gray, these lines here that are gray, that's nodal lines. Okay, so right there, gray and gray and gray. These would be spots where you'd be in a canoe and there'd be nothing going on. So they're showing an antinodal line there, right beside it's a nodal line. So they have that one listed as the nodal line, and that's a interference pattern, two-dimensional interference pattern. So it's a two-dimensional standing wave. Connecting some of the things together from the course. That's a little weirder, but you can actually see something like this even just with weird overhead printouts of circles. You see how you get the sort of spots where you get, this is just kind of trippy, but you know, it's sort of the same. You get spots where things are adding up and not. So just for fun, I showed that. But anyways, so main idea, yeah, we got reflection and diffraction and refraction and interference patterns and so on. Okay, so hopefully that makes sense. And there's your questions. And if you have any questions that you need me to do more about, please post in our, go to it here. I'll just show quick our post help questions area, right? So I'm just going to show you because I was an announcement in earlier today that there's 3 questions in there and the number of people that have viewed them is very low. That worries me because I want you to get the help that you deserve. So that's the most recent one I put in. 1 view, 6 views on this one apparently, but like yeah, there should be like 27 or 30 views, however many people are in the class right now. Really, right? There's a new post, watch for it. Okay, so you just go to the post questions link, and if you ever want to do like a synchronous help thing, just click that. Let me know when you're going to do it, of course, and we'll meet up at a certain time. You click it, I click it, and next thing you know, we're in a little Teams meeting, and yeah, you can just ask questions directly. I can share my screen. I can write on the touch screen or smart board, just like if I was writing on a piece of paper in front of you if you were in school with me. All right. So hopefully that helps. Hopefully everything's working for you. Again, my goal here is to have this be as much like a normal in-person class as possible to make this as easy as possible to learn this interesting but sometimes challenging subject. All right. There you go. And we'll talk to you later. Thanks for watching.